All right, welcome to our tutorial on offline reinforcement learning, from algorithms to practical challenges. This tutorial will be presented by myself, Sergey Levin, as well as Aviral Kumar. I am an assistant professor at UC Berkeley, and Aviral Kumar is a PhD student at UC Berkeley. All right, well, let's get started. So I'll start this tutorial with kind of a big question and a simplistic answer. What makes modern machine learning work? Of course, there are a lot of complicated answers we could give, but if we had to simplify it down to just two things, I think we could probably say that a really significant part of the effectiveness of modern machine learning is the ability to utilize large and diverse data sets and high capacity and expressive models, like large neural networks. And this basic recipe has succeeded in a range of domains, from recognizing any image of any object in the world, to translating any language to any other language, to recognizing speech. And time again, the recurring theme and the most effective methods for these kind of recognition problems is the availability of large data sets and powerful high-capacity models. So where does that leave us with reinforcement learning? Well, reinforcement learning is, at its core, an active learning paradigm. You have an agent that interacts with the world, collects some experience, utilizes that experience to improve its model, value, function, or policy, and then repeat the process. And this is done many times. Now, we've seen reinforcement learning succeed in a range of domains, from playing video games to basic robotic manipulation skills and even beating the world champion at Go. So it's fair to say that reinforcement learning, when combined with high-capacity models, can be very effective. But if we look at realistic open-world settings, like the kind that have been tackled successfully with machine learning methods in the supervised learning domain, the kind that require those large data sets and big models, we see a really big gulf. It's not a gulf of asymptotic performance, is really a gulf of generalization capability. Reinforcement learning typically has been successful in closed world, relatively narrow domains. And the kind of generalization that we've seen in supervised learning has proven to be elusive. And perhaps there's a good reason for it. If in order to attain that kind of generalization, you need to use large and highly diverse data sets, and you have what is fundamentally an active learning framework, that means that each time you update your model, policy, or value function, you may need to recollect your entire data set. If you would like to, for example, use reinforcement learning to train an autonomous vehicle using real-world data, maybe the vehicle needs to drive in San Francisco and New York and London and Beijing. When the policy of the vehicle changes, does it have to then again visit San Francisco and New York and London and Beijing? That kind of recipe would simply never scale. This basic fact is also part of the reason why in reinforcement learning, far more so than in other machine learning areas, we've seen a lot of emphasis on simulated training, the use of transform simulation, and other techniques of this sort that basically try to get around having to utilize this active learning framework with real-world data. But of course, with all of these techniques, they're in a sense crutches to make up for the inability to utilize large real-world data sets, and the one formula that seems to have worked time and time again everywhere else is that large data sets plus large models results in meaningful and useful generalization. So can we somehow bridge this enormous gulf? Can we make it possible for reinforcement learning algorithms to utilize large and expressive real-world data sets without having to rely on extensive manual engineering, without having to rely on simulation and other such techniques that have proven to be unnecessary in other domains? So in short, can we develop data-driven reinforcement learning methods? So that's really going to be the topic of this tutorial. Conventional, classic on-policy reinforcement learning operates in a setting where you have a policy that interacts with the environment to collect some amount of data from one transition to multiple rollouts, uses that data to update the policy, and then collects new data. The term off-policy reinforcement learning is typically used to refer to algorithms that can utilize data collected by other policies. However, such offline reinforcement learning algorithms still operate in a regime where they will collect additional data as they go. So perhaps you have a policy that interacts with the world, collects some number of rollouts, adds those to a buffer, and then uses all the data from the buffer to update the policy. However, new data is typically still added to the buffer with each successive policy. The term offline reinforcement learning refers to the setting where new data is not added, where we have a fixed data set collected by some behavior policy, which I'm going to denote pi beta, and typically this behavior policy would not be known. It might not even be a reinforcement learning policy. It could be, for instance, data from humans. It could be data from some hand-engineered system. We typically wouldn't know what it is. It goes into a data set, denoted here with D, which is used to learn a policy. And that policy is trained without any deployment. If such a class of methods would work effectively, then we could truly have data-driven reinforcement learning methods. The term offline reinforcement learning is kind of a relatively new term, but the basic idea is actually quite old. And older literature also often uses the term batch reinforcement learning to refer to this setting. Much of the material in this tutorial, I should say, will also follow a tutorial and review that we've written together with Alvar Kumar, as well as George Tucker and Justin Fu, which is linked at the bottom of the slide. All right, so if we can design these kinds of offline reinforcement learning algorithms, then we could envision a new class of reinforcement learning techniques, ones where instead of having this active data collection paradigm, we would instead have a setting where maybe your agent has collected a wealth of past experience, perhaps from a variety of its previous tasks, or perhaps data that was given to it by humans or existing hand-designed policies. That data would be used to train up a model or a value function or policy to perform some desired task, and potentially the process could then further fine-tune with additional online interaction, but crucially we want the offline phase to produce some basic level of competence, attain generalization, and utilize all that highly varied and diverse data. If we can succeed at this, then we could not only allow current reinforcement learning techniques to generalize more widely, but we could also imagine applying reinforcement learning to domains where currently it's considered to be infeasible. So we could not only get reinforcement learning to enable robots to fix some electronics, but we could also imagine, for instance, taking data from doctors prescribing medications and use offline reinforcement learning to train an algorithm to suggest treatment plans. We could take scientific experimentation data and suggest plans for constructing experiments, data from power plants regulating energy production, regulation of chemical plants, logistics networks, all sorts of application domains where we would like more optimal decision-making, but where active online interaction and exploration is too costly, infeasible, or dangerous. All right, so in this tutorial, we're going to begin with a short primer on reinforcement learning. Those of you that are already reinforcement learning experts could fast forward through this section, but in order to get everybody on the same page, I'm going to take a few minutes just to introduce some basic reinforcement learning algorithm concepts. Then I'll discuss the offline reinforcement learning problem and cover some classic batch reinforcement learning algorithms, including methods based on importance sampling and methods based on linear function approximation. Then, overall, we'll describe a number of modern offline reinforcement learning algorithms, as well as methods for off-policy evaluation and model selection. I will then talk about how we should evaluate offline reinforcement learning methods, in which situations we might expect them to work well, and how can we think about benchmarking such techniques. And then overall we'll conclude, provide some discussion, and discuss some open problems in this area. All right, let me start with a short primer on reinforcement learning methods. So first, terminology and notation. In reinforcement learning, we have an agent and we have an environment. The agent interacts with the environment in a temporal sequential process. The agent selects actions at every time step, the action is denoted with the letter A, and the environment responds with the resulting state S, as well as with the reward that the agent should receive for that transition, which is typically considered to be a function, a scalar function on states and actions that is unknown to the agent but observed each time a transition is taken. The goal of the agent is to acquire a policy, pi, which is a distribution over actions conditioned on states. The resulting sequential process can be visualized with this graphical model. We have an initial state distribution P of S1, a transition probability P of ST plus 1 given ST-AT, which is unknown to the agent, and the policy pi of AT given ST. Importantly, the state obeys the Markov property, which means that the future is independent of the past, or put another way, the states and actions together define a Markov chain induced by the policy and the transition probabilities. The objective in reinforcement learning is to acquire a policy that maximizes the expected value of the total reward in expectation under this probabilistic model. So here, d pi of S is the state distribution under pi, basically the distribution over states induced by the policy pi and the dynamics p. And gamma here is a discount factor, so typically, especially if we consider infinite horizon RL, we would discount rewards further into the future according to an exponential scaling. The time horizon could be infinity. I will typically use a finite horizon in my derivations, but keep in mind that capital T could be infinity and everything should work out just as well. So some concrete definitions. S is a discrete or continuous state. A is a discrete or continuous action. I will use the symbol tau to denote a trajectory, which is simply a sequence of states and actions. And a policy induces a trajectory distribution, which I will denote as pi of S0, A0 through ST-AT, which is just the product of the initial state probabilities and the product over all time steps of the policy probabilities and the transition probabilities. And I will sometimes use the shorthand pi of t to denote the trajectory distribution. D superscript pi of ST is a state marginal of pi tau at t. And if I omit the subscript t, that denotes the overall state distribution, which you can think of as the weighted average of d subscript t superscript pi over all time with a discount. This is also sometimes referred to as the visitation frequency, and you can basically think of it as what portion of the time does the policy spend in each state overall. All right, so now let me describe a few basic reinforcement learning algorithms, and we will actually use much of the terminology and concepts when we talk about offline reinforcement learning methods later. One of the most basic reinforcement learning algorithms that I can describe is the policy gradient algorithm. So let's take our reinforcement learning objective, and our goal is to train a policy, which will be some function approximator, such as a neural network, that takes in the state ST and outputs a conditional distribution over actions given the state. And this policy has parameters, which I'm going to denote theta. So we can write it also as pi theta AT given ST. We can then write down an objective on theta. We can say we have an objective j of theta, which is the expected value under the trajectory distribution induced by pi theta of the total discounted reward. So that's the same thing as the RL objective at the top, but I've made it more explicit that this is now a function of theta. As the name might imply, direct policy gradient refers to calculating the gradient of j of theta with respect to theta. So if we want to just estimate the value of j of theta, we can simply average together samples from the trajectory distribution and average together their rewards. The way we can obtain those samples is simply by running the policy in the real world. So if we want to know what j of theta is, we might run the policy, let's say 50 times, and average together the discounted rewards along those 50 trajectories. We refer to such samples as rollouts, colloquially. But of course, we don't just want to evaluate what j of theta is, we want to figure out its gradient. So the gradient of j of theta can be written as also the expected value under pi theta of tau of the gradient of the log probability of the trajectory times the total reward. There's a simple algebraic derivation of this, which I won't go through in this tutorial, but it's pretty straightforward. Once we've done this, we can substitute in the definition of the trajectory distribution for log pi of tau and write it as follows. The gradient is equal to the expected value under pi theta tau of the sum over time of the grad log probabilities of each of the actions times the sum over time of the rewards. And this just follows from the definition of tau and the definition of the trajectory distribution. we can further take one of these sums, specifically the sum over rewards, and distribute it inside the sum over log probabilities. And when we do this, we can make use of the fact that the policy at time step t will not affect the reward at preceding time steps. Basically, no action you take today will change what happened yesterday. So we can therefore change the summation over the rewards. Instead of summing from 0 to capital T, we can sum from T to capital T. And this gives us somewhat lower variance. And this form of the policy gradient is close to the one that people would use in practice. Oftentimes when we write out the policy gradient, we replace the sum of rewards with the symbol Q hat of STAT. Q hat here denotes our estimate of the expected total reward we'll get if we take action AT in state ST and then continue with our policy pi theta. So how would we implement policy gradients in practice? Well, in practice, the same way that we estimated J of theta using samples, we would estimate grad theta J of theta using samples. So the resulting algorithm, which is often referred to as reinforce, following Williams' original paper, works like this. Sample some trajectories from your policy by just running the policy, rolling it out in the world. Estimate the gradient using the formula above and the samples you've just generated, and then take a gradient ascent step with some learning rate alpha. So intuitively, you can think of this process as generating some rollouts, estimating the rewards of those rollouts, and then increasing the log probability of the actions along the good rollouts, and decreasing the log probability of the actions along the bad rollouts. So that completes our discussion of the basic policy gradient, but let me talk a little bit more about this Q hat thing. What is this Q hat really, and what do we want it to be? Well, Q hat is some kind of estimate of what we refer to as the Q function, also sometimes known as the state action value function. The Q function is the expected value of the total reward or total discounted reward that you will get if you start in state ST, then take action AT, and then follow your policy. Similarly, the value function is the same thing, but conditional on only a state ST. Q functions and value functions are tremendously useful objects in reinforcement learning, and we will use them repeatedly in our discussion of offline RL algorithms. These are really, really useful. Indeed, if we have the Q function, we can rewrite the policy gradient not as an expected value over trajectories, but instead in terms of the state probabilities. And the way that we do that is we write it as the expected value under d pi theta of S and A distributed according to pi theta of A given S of grad log pi of that action times the Q value for that state action pair. And we multiply by 1 over 1 minus gamma in front to account for the fact that we are no longer summing over all the time steps. Of course, in practice, it's a constant, so if we're optimizing, we can disregard that constant. The Q function follows what is called the Bellman equations. So we know that Q pi of STAT is equal to the reward at STAT plus gamma times the expected value over the next state and the next action of the Q value at the next state and action. And this Bellman equation provides us with a way of training a function approximator to estimate the Q function by minimizing the difference between the left-hand side and right-hand side of this equation using all of our data. And that can give us better estimates of the Q function than just using a single sample like we did in the policy gradient. To simplify this equation, I can omit all those superscripts since you know the expectation is over now. So in the remainder of the tutorial, we'll typically write the Bellman equation in some form like this, where I've just omitted the subscripts. All right. Now, one of the things we can do once we've defined Q functions like this is we can extend our policy gradient method into an actor-critic algorithm. In an actor-critic algorithm, we're going to estimate the Q function for some policy pi theta. In the tabular case, we would actually set Q pi theta for every state in action to be the current reward plus gamma times the expected value of the next Q function. And then we would use this inside the policy gradient formula to get a better estimate of the policy gradient and update our policy parameters. More generally, you don't have to calculate the Q function exactly in step one. You could update the Q function if it's represented by a parametric function approximator to simply reduce the difference between the left-hand side and the right-hand side of this equation. A very common technique is to actually take the squared difference of the left-hand side and right-hand side and compute its derivative. But of course, this begs the question, under which distribution should we estimate this error when we're training the Q function? For now, we'll just say that we do this under the same distribution as our current policy. This is the on-policy setting. But later on, this is precisely the distribution that we're going to vary, and we'll see that we actually get quite a lot of additional complexity when this distribution is no longer d pi theta. And of course, in general, step 2 and 3 just need to improve pi theta with respect to the expected value of q pi theta using some method. It doesn't have to be a policy gradient, although policy gradient is a reasonable choice. So the general actor-critic with function approximation would have two function approximators, one which takes the state and outputs a distribution over actions given the state and has parameters theta, and a second one that takes the state and the action and outputs the q value and has parameters phi. And in general, we could proceed like this: update q phi to decrease the expected Bellman error, update pi theta to increase the expected q values, and repeat. So this is kind of the basic sketch of a generic actor-critic algorithm. So now let's talk a little bit about switching to the off-policy setting. In the off-policy setting, the update to pi theta and the update to q phi would both use data that is drawn from some other distribution, and I'm going to call that d pi beta. Is it still correct to do this? Can we just replace the distribution over states in the expectation with some totally different distribution? Is this still correct? Well, in general, not exactly. And we'll discuss this a lot more when we talk about importance sampling later. But in practice, this kind of thing could work if you repeatedly collect additional data from your policy. I'll talk about some of the problems that happen in the fully offline setting later, but there is a wide range of off-policy actor-critic algorithms that are very widely used today that do use a different distribution, d pi beta. Typically, this distribution is formed by taking the aggregation of all previous policies. So in these kinds of algorithms, we would have a data set of all the transitions we've seen so far, also referred to as a replay buffer. We do off-policy learning on this buffer for both q phi and pi theta, and then periodically we interact with the world using our latest policy to add fresh data to the buffer. Now, we could also remove the policy entirely by having the policy essentially be implicit, and this would give us a q-learning or fit-a-q iteration algorithm. The way that we would do this is we would remove step 2 and replace it with an implicit policy where we choose pi by setting it to be the policy that takes an action with probability 1 if it's the argmax of the q function and probability 0 otherwise. But the same conceptual framework applies. So especially in cases where you have discrete actions, this is a very practical way to do things, and this is the basis of q-learning and fit-a-q iteration. Everything we discussed before, however, still applies. Okay, so now that we have this whirlwind tour of the basics of reinforcement learning methods, let's talk about the offline reinforcement learning problem statement and a little bit about why it's difficult. So what does offline RL really mean now that we have the notation for reinforcement learning? Well, as I said before, in on-policy reinforcement learning, your policy always uses the latest data from its latest interaction. In off-policy reinforcement learning, as I mentioned before, all of the data collected so far by all of the past iterates is accumulated into a replay buffer and reused, and this can greatly increase efficiency, but it's still inherently an active and online process because you would still be collecting data using your latest iterate, pi k. In offline RL, the data is collected only once using some behavior policy pi beta, which is in general not even known to you. So you're just handed a data set of transitions Si, Ai, Si prime, and Ri, and you have to use this data set without any additional environment interaction to acquire the best policy you can get. So formally, the data set is a set of tuples Si, Ai, Si prime, Ri, where Si prime was the sample of the next state obtained by taking action Ai in state Si, and Ri was the reward that was associated with that transition. We assume that the states in this data set are distributed according to some unknown distribution d pi beta of S, which is induced by the state distribution of an unknown policy, pi beta of A given S. More generally, we might not even assume that this policy is Markovian, so it could be pi beta of A given anything. The next state, of course, has to be drawn according to the correct environment dynamics probabilities, which we also don't know, but we assume that they're the same. And the reward comes from the reward function, also unknown, but also consistent. The RL objective is still the same. Our goal is still to find a policy that will maximize the expected reward when we actually run it in the environment. But we are not allowed to run it in the environment during training. We can't actually perform those rollouts that I mentioned before, and that's what makes offline RL so much more difficult. So at this point, we might ask some high-level conceptual question, like, how can you even do this? Like, is it even possible to get something sensible in the offline RL setting? Well, in short, yes. There are a number of reasons, some a bit simpler, some a bit more nuanced, why offline RL should be possible. First, even if your dataset contains a variety of different behaviors, some of them might be better than others. So simply finding the good stuff in a dataset full of good and bad behaviors could already result in offline RL acquiring a better policy than the one that was used to generate the data. Second, you might get meaningful generalization. Good behavior in one place might suggest good behavior in another place when your function approximator generalizes effectively. Third, there is a stitching effect that is possible. Parts of good behaviors in different places can be recombined such that even if you've never seen a single trajectory that performs the entire task, if you've seen parts of trajectories that perform parts of a task, you can recombine them in new ways. For example, if your training set contains some trajectories that go from A to B and some trajectories that go from B to C, you can combine these parts to figure out how to go from A to C. Here's a concrete example of this. Let's say that we have a data set where this green circle is navigating a maze. Now, crucially, the green circle keeps going to different places. So maybe it never performs the task we really want. The task we really want is to go from the upper left corner to the lower left corner to the upper right corner. The green ball never does that, but it goes through all sorts of other different junctions in the maze. So this gives us a data set that is sufficient to understand how to navigate the maze, what kinds of navigations are possible, so that when we are then given a goal to navigate from the lower left to the upper right, we can recombine parts of the behaviors we saw in our data set to learn to perform this task, even though we've never actually seen this entire trajectory in the data set. All right, so why should we care about all this? Well, remember that in reinforcement learning, you have an agent that needs to interact with the world many, many times. And this can be very impractical if you want to learn from large data sets, because you have to recollect your data sets every time you update your model. If you want to acquire robotic skills that generalize broadly, or learn from data where online exploration is impractical, like the medical diagnosis setting, or settings where experimentation is just too costly. For instance, if you are a large e-commerce company and you want to do inventory management, you probably don't want an RL algorithm doing trial and error learning on the inventory in all of your warehouses, but you probably have a lot of historical data. Similarly, autonomous driving. Very hard to imagine active learning style methods like reinforcement learning being used for autonomous driving today because of the exploration issues. And I think it's fair to say that a lot of folks that are thinking about autonomous driving with RL are thinking about it in terms of simulation. But offline data in this setting is readily available from human drivers. All right, so does this basic recipe work? Can we actually do offline RL? I'm going to tell you about a little case study that we've done a few years back. This was a project on robotic grasping, where that maybe sheds a little bit of light on what happens in the offline learning setting. So in this project, which is called QT-Opt, the idea was to develop a general framework for learning robotic manipulation from images using real-world data. The algorithm was essentially a fancy version of the fit-a-Q iteration method that I've already outlined, so very similar principles, and training was performed where large data sets were collected from many previous RL experiments, and we could either train a policy entirely from that offline data, or we could perform some additional online fine-tuning. Now, the basic system trained with this method actually worked really well. So it was able to pick up a wide variety of different objects directly from monocular RGB images. So here you're seeing the robot executing its learned grasping behavior from dense clutter, even in the presence of humans who will perturb it in various nefarious ways. So, the basic idea basically works. Like reinforcement learning can generalize when provided with sufficiently diverse and large data sets. It could pick up new objects that it's never seen before, kind of all the stuff that we would want a deep learning system to do. But one question that we tried to answer in the paper, this was a little bit of a side note because the project was primarily focused on robotics, but it's very relevant to this tutorial, is what happens when we do pure offline training versus if we do some additional online fine-tuning. So the data set for offline training consisted of 580,000 offline transitions. The additional online fine-tuning involved just 28,000 additional transitions. So the additional data was very, very small. So if there's a difference, it's not because of the data set size, but simply because of the provenance of the data, the fact that it is really online collection. The success rate for the fully offline method on a test set of previously unseen objects was 87%. The success rate with fine-tuning was 96%. Now you might say, well, maybe that's not such a big difference, like 87 is a pretty big number. But if you look at the failure rate, basically take 100 minus that number, the failure rate is more than 3 times larger for the offline method. So something is happening, generalization is pretty good, but there's this big price that we're paying for not having that online fine-tuning. And the data set here, let me tell you, the data set was good. It was a very good data set. It was very diverse, very broad. So if something here is not working as well as it should, it really seems like it's probably an algorithms issue. So why is offline reinforcement learning hard? Well, there are a number of issues that we have to contend with. One big issue is feedback. Feedback is a problem anytime when a deployed machine learning system affects what it will see next, which is of course the case in a sequential decision process of the sort that we see in RL. So when we use a learned model to act, it changes what we see. Here's a simple example. Let's forget about RL, and let's imagine we have an even easier problem. Let's say that we're given a data set that contains optimal actions. Not just any old actions, but like literally just the optimal actions. All we have to do is just copy the actions that were taken. Well, the trouble is that when you train on those optimal actions, your learned policy pi theta will make some small mistake. And when it makes a small mistake, it'll find itself in a state that is different than the states that were seen during training. And then it will make a bigger mistake. And then it will find itself in a state that is even more different than the states that were seen during training, and these mistakes will compound until after a while, the policy will diverge wildly from those optimal actions seen in the training data. Indeed, it's known that the error in this process scales as O of t squared, and this is discussed in a landmark paper by Ross et al. Called The Reduction of Imitation Learning and Structure Prediction to No-Regret Online Learning. Now, of course, we're not doing behavior cloning here, but arguably we're doing something harder. So if even the behavior cloning case has this problem, we're going to have feedback issues as well. Now, we studied the problems with offline reinforcement learning in a paper by Avral Kumar, Justin Fu, George Tucker, and myself called Stabilizing Off-Policy Q-Learning via Bootstrapping Error Reduction. And we had a few hypotheses about what might be wrong. So one hypothesis we had was, well, maybe you're getting some kind of overfitting effect. Maybe when you're not allowed to collect more data, you just overfit to the data you collected initially, and bad stuff happens. So to evaluate this, we varied how much training data was available to a naive offline, in this case, actor-critic algorithm for a standard benchmark, in this case called the half-cheetah. So the blue curve has 1,000 data points, the red curve has 1,000,000, and you can see that they're doing about the same. So if increasing the amount of data doesn't reduce the problem, it seems unlikely that the problem is overfitting. We then asked the learned Q function how well it thought it was doing, right? Remember, the Q function is an estimate of the expected reward to go, so you could interrogate your Q function and ask it, does it think it's going to get high reward? So this is what the Q function thinks it's going to get. And notice here that the y-axis is actually a log scale. So for that data set of 1,000 transitions, it thinks it's going to get 10 to the 20th power, but instead it gets minus 250. That's quite a big difference. So something is off here. It thinks it's going to do really well. We had some other hypotheses. They're not that interesting. We thought maybe the training data is not good. And that's usually not the case. Behavior cloning the best data actually sometimes does better than these naive algorithms. So something is going on here. The algorithm is messing up, and it's deeper than just overfitting or bad training data. It turns out the issue really comes down to distributional shift. So here's sort of distributional shift in a nutshell. When you solve some kind of supervised learning problem, basically an empirical risk minimization problem, let's say that you're minimizing the difference between f theta of x and some true value y in expectation under some distribution p of x. You could then ask, given some x star, is f theta of x star correct? Well, if you don't overfit, you know that the expected value of the error will be low in expectation under your training distribution. So for new samples drawn from that same distribution, you'd expect the error to be low. But in general, you can't expect the error to be low if under some other distribution p bar of x if p bar is not equal to p of x. There are, of course, bounds you can show if p bar is very close to p, but if they're different, in general, all bets are off. In fact, even if x star is drawn from p of x, in general, bounding worst-case performance is very difficult. Now, you might say, usually we wouldn't be worried about this. See, we're doing deep learning. We've got these deep nets, and they generalize really, really well. In some cases, that might actually be true. However, let's consider a slight twist on this. What if x star wasn't just chosen arbitrarily? What if it was actually chosen to maximize your learned function f theta of x? So let's say this green curve is the true curve, blue is your fit. Your fit is pretty good in most places, but what happens if you select the x where f theta of x is largest? Well, you get the point with the largest error. In a sense, optimizing with respect to the input to your learned function approximator is a lot like generating an adversarial example. It's finding some input x for which your function approximator predicts the largest value. Typically, this will be the largest mistake in the positive direction. So even if you believe that your deep net will generalize wonderfully well, if the x's are selected via optimization against your deep net, it is very, very hard to combat this. So where do we suffer from distributional shift in reinforcement learning? Well, let's come back to our Bellman equation. And I have it written here for the Q-learning setting, but the same thing applies in the actor-critic setting. In fact, let me just rewrite it in the actor-critic way. I'll say that your target value has an expectation over A prime according to some distribution pi nu. If you're doing Q-learning, you would select pi nu to be the greedy policy with respect to Q. If you're doing actor-critic, this would be your new actor. And let's call the right side of this equation y of SA. So your target values are y of SA. What is your objective for training the Q function? Well, in the off-policy setting, it would be to minimize the difference between the left-hand side and right-hand side of the Bellman equation in expectation under some distribution pi beta. And pi beta is your behavior policy. So that means that our Q will be close to y in expectation under pi beta. So we expect good accuracy when pi beta is equal to pi nu. Right? Because on the left-hand side, we're evaluating the expected value of Q under pi nu. But how often is that the case? The whole point is to get a better policy pi nu that is different from the behavior policy. Different hopefully in a good way. The situation is actually even worse because pi nu is selected to maximize the expected value of Q. Think back to our actor-critic algorithm. We select pi nu to be the argmax of the expected value of Q. So just like on the previous slide, we're essentially picking the policy that results in actions that are adversarial examples for our Q function. And that explains why the Q function doesn't do so well, but thinks it's doing fantastically. Where else do we suffer from distributional shift in the offline setting? Well, we have the same drift problem that we have to contend with in the behavior cloning case. Our state distribution induced by a policy, d pi theta, in general will not be the same as a state distribution induced by our behavior policy, d pi beta, which means that even if pi theta is great on the training data, it might be bad when we actually use it for control. So we have in addition a state distribution mismatch when we actually run the policy. And we also have sampling and function approximation error, just like we do in the on-policy case, except that now it's a little more problematic. So let's say in the online RL setting, you fit your Q function or value function. Let's say the green dots represent your points, and you extrapolate a little bit and think that you have a really good value right over there. That probably means that when you then go and collect data, you will sample that point, and if it is bad, it'll serve as a very good counterexample, a kind of hard negative, to fix your estimate. But of course, in the offline setting, that fix doesn't happen. So existing challenges with sampling error and function approximation error in standard RL become much more severe in the offline setting. All right, so in the next section of the tutorial, let me talk a little bit about a number of classic batch reinforcement learning algorithms, basically how have people thought about these problems in the past, and then afterwards, overall, we'll talk about some modern algorithms that strive to address some of these distributional mismatch problems. So one pretty broad class of batch or offline reinforcement learning algorithms extends on the policy gradient framework. So in order to calculate the policy gradient in the manner that I described before, we need to generate samples from pi theta. So our gradient with respect to theta of j theta is approximately equal to the average over samples from pi theta of the sum over time of the gradient with respect to theta of the log probabilities times this q hat. But what if we only have samples from some other distribution, pi beta? Well, one common trick we can employ if we want an expected value under one distribution, but we have samples from another, is to employ importance sampling. So we put in this importance weight, pi theta of tau I, divided by pi beta of tau I, and this is an unbiased, consistent estimator for the policy gradient. But it's a very high variance estimator in practice. So let's look at the importance weights a little more closely. And by the way, it's worth pointing out that q hat here is just a sum over future rewards for the policy pi beta in this case, so we'll come back to that later. But first, let's expand out our importance weights. So if we substitute in the definition of the trajectory distributions, we see that the numerator has p of s1, a product over time of all the transition probabilities, times pi theta of at given st, and the denominator has the same thing, only pi beta in place of pi theta. So that means that the initial state probabilities and the transition probabilities cancel out, which is very good news for us because we don't know what they are. We do need to know what pi beta is. You can't use importance sampling if you don't know what pi beta is, but as long as you know what it is, then you can calculate these importance weights. Unfortunately, these importance weights are going to be exponential in the horizon capital T because you're multiplying together capital T probabilities, each of which are going to be less than 1, which means that as t increases, your overall numerator and denominator will go to 0 exponentially. And that's why importance sampling in the RL setting, at least when done in this way, has very poor numerical properties. So the weights are very likely to be degenerate as capital T becomes large. So can we fix this somehow? Well, in short, no, but there are a number of steps we could take to try to mitigate the problem. So to get into how this is done, first it's very useful to break up this product over action probabilities into two parts. The first part goes from 0 to t minus 1, and the second part goes from t to capital T. Now, of course, you multiply these together, you get the original product from 0 to capital T, but I'll break them up into two parts, and I'll put the first part in front of the grad log pi, and the second part in front of the q hat. And the reason I'm doing that is because intuitively, the role of these two halves is a little different. The first half essentially accounts for the fact that your new policy pi theta might not get into the same state action tuple as your behavior policy pi beta, so it accounts for the past. Essentially, pi beta might have landed in some state that pi theta is very unlikely to land into, and the product of all the actions that led to that state can serve as a proxy for detecting when that happens. So you can sort of think of that first product as estimating how much more or less likely pi theta is to end up in state st and end up taking action at. The second product accounts for the fact that q hat is an estimate of the value of pi beta, not pi theta. So that's correcting the value. It's essentially accounting for the rewards in the future. So the first part accounts for differences in probability of landing in the state st. The second part accounts for having the incorrect q hat. Now we could disregard the first part. It turns out that if pi theta and pi beta are sufficiently close to each other, disregarding the first part results in limited, bounded error, in fact, and it's still possible to make progress. And this is a very common thing to do. We can't really disregard the second part, though. So why is disregarding the first part a reasonable approximation? Well, intuitively, if pi beta lands in similar states as pi theta, we'd expect this to work out all right. More formally, you can actually prove a bound in terms of the divergence between pi theta and pi beta, between the return using one estimator versus the other. Okay, but the second term is a little more problematic. We can't get rid of the importance weights there. So that's why in much of the literature, the focus really is on better estimation of values using importance sampling. Okay, so how can we estimate these returns? So right now, Q hat is an estimate, what we want it to be is an estimate of the expected reward under pi theta, and that's why we apply the importance sampling correction. All right, so one thing we could do is we could take into account the fact that Q theta is a sum of rewards over time, and we could distribute the importance weight inside the sum of rewards. So basically replace Q hat with a sum over time of gamma to the t minus 1 to the t prime minus t times rt prime, distribute the product inside, and then note that all those future probabilities, the ones that come after t prime, aren't going to affect the reward of t prime. So you can change the variables that you're taking the product over to not go from t to capital T, but instead go from t to t prime. Now this is still exponential, but for the earlier rewards, you're multiplying together many fewer numbers. If you want to fully avoid exponentially exploding importance weights, you have to use value function estimation. So no importance sampling trick will fully avoid this exponential blowup, but you can mitigate it. So if you somehow knew Q pi theta, you would just substitute that right in. And that's what we'll talk about in the next section. But first, let's conclude our discussion of importance sampling by noting a few other ways that people have thought about this problem. So one concept that I want to mention here is something called the doubly robust estimator. The doubly robust estimator doesn't do away with the exponential blowup, but it does reduce the variance. So first, I'm going to simplify my notation a little bit. So this thing is exponential, that's our value estimate. I'll simplify my notation by summing from t equals 0. I'll just assume without loss of generality that the current time step is 0. I'll replace t prime with t and t double prime with t prime, and I'll drop the subscript I. This will just declutter my notation. So the value at some state s0 is just the sum over time of the importance weights up to that time step times gamma to the t times rt, which is the reward that pi beta got at that time step. And I'll just use the symbol rho t to denote the importance weight to further declutter my notation. So this gives me this very simple way of writing the importance sampled return estimator. And what I can then do is I can expand this sum and product. And this is going to obviously look messier, but it's going to be suggestive of a particular recursive relationship. So if I actually write out the sum of products, I get R0, rho 0 times R0 plus rho 0 times gamma times rho 1 times R1 plus rho 0 times gamma times rho 1 times gamma times rho 2 times R2 and so on and so on. And if I group these things together, I can see that this has kind of a neat recursive structure. It looks like rho 0 times, in parentheses, R0 plus gamma times, in parentheses, rho 1 times R1 plus gamma, etc., etc. So I can write it as some recursively computed quantity, which I'm going to call V bar capital T, where V bar capital T plus 1 minus T is equal to rho T times RT plus gamma V bar capital T minus T. So we can just compute all these V bars recursively, and we'll get this importance sample estimator. Okay, that by itself doesn't change anything. I haven't actually changed the estimator in any useful way. This is just another way of writing it. But now we're going to bring in a very useful concept called the doubly robust estimator. Here is the doubly robust estimator for the bandit case, the case where there's only one time step. So just to clarify what's going on here, you had a sample from some other policy pi beta, which resulted in the reward RSA, and it has the importance weight rho SA. And then you have some model of the return, Q hat SA. Maybe it's obtained by training a value function or by training a model and doing some model-based evaluation. Q hat SA is your function approximator. V hat SA is the expected value of that under your new policy pi theta. You can get a better estimate, the doubly robust estimate, by taking your V hat S. Now V hat S might be biased, so then you add your importance sampled estimate, but you subtract off Q hat SA to account for the fact that you're adding V hat S. Those of you that are familiar with control variates will recognize this as essentially the same concept. So to apply this idea to the sequential setting, we can apply the doubly robust estimator to V hat, to V bar. So if we have some V hat and Q hat, we can basically change the recursive relation of V bar to introduce V hat and Q hat. So this is the result from Zhang and Li that applies the doubly robust estimator to the sequential setting. This doesn't get rid of the exponential problem, but it does, in principle, reduce the variance. Okay. Another concept that has been explored in the literature to mitigate some of the issues with importance sampling, which can, in principle, address the exponential issue, is marginalized importance sampling. So here, instead of calculating a product of action probabilities, you instead estimate an importance weight on state probabilities. Now, computing state marginals, d pi theta and d pi b, is in general very difficult, but in many cases you can compute the ratio of those marginals more tractably than computing the marginals themselves. So if you can calculate these state or state action importance weights, these marginal importance weights, then you can estimate your return that way. Now, typically this is done for off-policy evaluation rather than policy learning, but you could imagine this is a way to get those Q estimates as well. How do we determine the weights? Well, typically most algorithms in this area, which I won't have time to go into in detail, solve some kind of consistency condition. So one example of a consistency condition, this is from a paper by Zhang et al. Called GenDice, is a relationship that is obtained by writing out the flow equations, the occupancy measure equations in an MDP, and then replacing d pi theta with d pi beta times w, right? Because d pi beta times w is just d pi theta. So if you can write occupancy measure flow equations and then replace d pi theta with d pi beta times w, then you get a condition on w expressed entirely in terms of quantities that you know or have sample access to. So you have the first term, which accounts for the probability of starting in that state, the second term that accounts for the probability of transitioning into it, just like the occupancy measure equations. And then you could turn this into a consistency condition and solve for the w's that are consistent. So typically this involves some kind of fixed point problem, and if you want to read more about this, I have citations on this slide. So on this slide I have citations to classic work on importance sampled policy gradient estimation, doubly robust estimators, some analysis and theory, and marginalized importance sampling. And we also discuss this in section 3.1, 3.2, 3.3, and 3.4 in our tutorial and survey paper. So if you would like to read up more on this, you can pause the video here and look up these citations. All right. The next kind of classic batch RL algorithm I'm going to talk about deals with value function estimation. So have people thought about offline value function estimation before? And how have they thought about it? Well, one line of work addresses this question by extending ideas for approximate element programming and Q-learning to offline settings, where you can derive some tractable solutions with simple function approximators like linear function approximators. This is perhaps less relevant for deep reinforcement learning, but I want to go over it because some of these algorithms reveal interesting trends and ideas in the literature that are worth knowing about. How are people thinking about it now? Well, these days, a lot more work in this area focuses on approximate solutions with highly expressive function approximators like deep nets, and the primary challenge turns out to be distributional shift. And generally, a lot of the more recent work is not concerned with quite the same issues. So the classic work typically doesn't really say anything about distributional shift and deals more with the offline estimation problem. More recent work deals with expressive function approximators and focuses on distributional shift. So maybe this distributional shift was just not as big of a problem with linear models, maybe because they had a tendency to generalize better or they were provided with good features. These days, that's actually a really big problem. So we'll discuss some older offline batch RL methods next for completeness, and then overall we'll talk about more recent methods that deal with distributional shift. So, and I should preface by saying a lot of this material is borrowed from some really excellent slides prepared by Ron Parr. As a warm-up, let's think about model-based reinforcement learning with linear models. So let's say that we have some feature matrix denoted phi, and the feature matrix is a matrix S by K entries. You could also think of it as a vector-valued function phi of S. So you can think of it as a matrix where the number of columns is the number of features and the number of rows is the number of states. And for each one you have a number denoting the value of that feature in that state. Can we do offline model-based RL in this feature space? Well, we can do it like this. Step 1, estimate the reward in terms of your features. Step 2, estimate the transition probabilities in terms of your features. Step 3, use that to recover a value function. And then step 4, use that value function to improve your policy. So the reward model, so all our models are going to be linear in the features because things were linear back in the day. So our reward model is going to be capital Phi times some weight vector WR. And we want this to be close to R. So WR is just a column vector with dimensionality equal to the number of features. One way we can solve for WR is with least squares. So these are just the normal equations for solving for WR with the least squares fit to the vector R, which is the vector of rewards. We're assuming for now that we have all the rewards, all the states, etc. But we'll look at the sample-based setting soon. So for now, we just assume that we have the reward at every single state. Samples will come later. The transition model, we want phi times some transition matrix p phi to be close to the effect that we get from applying p pi to phi. Right? So p pi is the true transition matrix obtained by composing the dynamics and the policy. So this is a transition model for a fixed policy. And p phi is a thing with which you want to approximate it. So p pi is the real transition matrix on states, so it's S by S. So this is basically the Markov chain on states induced by a given policy pi. And p phi is an estimated feature space transition matrix, which is k by k. So again, if we want to approximate p phi, we can do least squares and solve the normal equations. And again, plugging that in, this is just the normal equations for p phi. And just like before, we assume that we have tabular access to p pi, so we can calculate p pi phi exactly. Of course, again, that's an unreasonable assumption, and we'll get samples later on. Okay, so we've got our reward, we've got our transition probabilities, which means that we can estimate our value function with some linear equation, phi times WV. How do we get WV from WR and p phi? Well, as an aside, if you have a tabular reinforcement learning problem and you want to solve for v pi in terms of p pi and r, you can write v pi as r plus gamma p pi v pi. This is just the Bellman equation expressed in vector notation. And then you can solve this, right? So you have identity times v pi plus r plus something else times v pi. So throw that gamma p pi v pi term on the left-hand side. You get identity minus gamma p pi times v pi is equal to r. And then hit that with the inverse on both sides, and you get v pi is equal to identity minus gamma p pi inverse times r. So in the model-based case, we can do the same exact thing, but in feature space. So we can apply the same equation in feature space and say that WV is equal to I minus gamma p phi inverse times WR. Same exact logic holds. So that gives us an equation for WV. But wait, do we even need the model? So we were solving for WR and p phi. All we really need is WV. So what if we just substituted in the equations for WR and p phi directly into this equation for WV? So just substitute these in there. And if we do that, okay, we get a mess, we get an alphabet soup. If this looks like a confusing equation, don't worry, I literally just copy and pasted the WR and the p phi into that equation for WV. But with a little bit of linear algebra, I can simplify this equation to the following form. WV is equal to phi transpose phi minus gamma phi transpose p pi phi inverse times phi transpose r. Okay, much simpler equation. No more WR, no more p phi. We can directly solve for WV and skip the middleman. So it turns out that the model-based case is actually the same as the model-free case in this setting. And by the way, this equation for WV is exactly what you get if you do the least square solve to minimize the Bellman error. So this is called least squares temporal difference learning. Okay, so that's nice. We can recover WV. Can we do it all with samples? Well, in the case where we have samples, we don't have access to the entire vector R, and we don't have access to the entire matrix P pi. But we do have a data set of transitions, S, A, R, S prime, which we can assume has samples from R and samples from P pi. So the data set has to come from pi in this case. So now our matrices are no longer K by S, they're K by number of samples. We're going to replace P pi phi with the features of S prime, and I'm going to call that phi prime. And we're going to replace R with a vector of sampled rewards. But everything else actually works exactly the same way, only we now have some sampling error. So actually the same exact equation can still be used to solve for WV using samples, and virtually nothing changes. All right, so let's go back to our original outline and talk about that last step. How do we actually use this to improve the policy? So step 1, step 2, and step 3 turns out to be a lot simpler. You can just use LSTD. But step 4 is still an issue. So the typical policy improvement step would set the policy now to be the greedy policy with respect to phi WV, and then estimate V pi prime again. And the problem is that we assume that our data set comes from the policy pi. So if we're changing the policy, our data set is no longer valid, right? Those phi primes that we used required samples from pi. So this is not going to work for offline RL. This works for policy evaluation, but not for offline reinforcement learning. Fortunately, for offline reinforcement learning, we can get a viable algorithm with a small change. Replace LSTD with LSTDQ, which is LSTD for Q functions. And that will get us an algorithm called LSPI, least squares policy iteration. The idea now is that instead of a feature matrix that's S by K, we're going to have a feature matrix that's S times A, states and actions, by a new set of features, K prime. One way that we can get K prime, for instance, is by replicating our features for every action. So you have feature 1 for action 1, feature 1 for action 2, etc., etc. But you could also have action features if you prefer that. All right. It turns out that in that case, WQ can be written out exactly the same way as before, except that now phi is a state action feature matrix. But everything else stays exactly the same. Now we don't need the data set to come from any particular policy. We're evaluating a Q function. The only change is that when we calculate phi prime, we take the state that's actually in the data set, but the action from our latest policy. So we change how we calculate phi prime because we need to get the action from our latest policy, but everything else stays the same, and we get a Q function. So LSPI computes WQ for your current policy pi k, and then computes pi k plus 1 by taking the argmax of at every state of phi SA times WQ. And then sets phi prime to be the featurization with the action from the new policy. Okay, so this gives us a way to actually perform offline RL or batch RL with features. Now, why doesn't this by itself already solve all of our problems? Why can't we actually use this to solve all of our offline RL issues? Well, of course, one obvious answer might be perhaps we want to use deep nets instead of linear function approximators. But the issue actually goes a little bit deeper than that. So as I mentioned before, we have this problem with distributional shift, where when the actions from the policy change, the Q function is going to in general be very over-optimistic. And LSTD and LSPI don't really do anything to address this problem. So the problem will be that we calculate our target values, we optimize it under some distribution. LSTD has the same issue. It has some distribution under which it's doing least squares. So least squares minimizes error under a distribution, and that distribution comes from pi beta. We'd expect good accuracy when pi beta matches pi nu, but when it doesn't, of course, we're going to have issues. So in general, all approximate dynamic programming methods, fitted value iteration, Q iteration, LSTD, LSTI, they will suffer from action distributional shift, and we have to fix it. So that's what Aviral is going to talk about in the next section.